A leap second is a 1-second adjustment that is occasionally applied to Coordinated Universal Time in order to keep its time of day close to the mean solar time, or UT1. Without such a correction, time reckoned by Earth's rotation drifts away from atomic time because of irregularities in the Earth's rate of rotation. Since this system of correction was implemented in 1972, 26 leap seconds have been inserted, the most recent on June 30, 2015 at 23:59:60 UTC. The UTC time standard, which is widely used for international timekeeping and as the reference for civil time in most countries, uses the International System definition of the second, based on atomic clocks. Like most time standards, UTC defines a grouping of seconds into minutes, hours, days, months, and years. However, the duration of one mean solar day is now slightly longer than 24 hours because the rotation of the Earth has slowed down. Therefore, if the UTC day were defined as precisely 86,400 SI seconds, the UTC time of day would slowly drift apart from that of solar-based standards, such as Greenwich Mean Time and its successor UT1. The purpose of a leap second is to compensate for this drift, by occasionally scheduling some UTC days with 86,401 or 86,399 SI seconds. Specifically, a positive leap second is inserted between second 23:59:59 of the chosen UTC calendar date and second 00:00:00 of the following date. This extra second is displayed on UTC clocks as 23:59:60. On clocks that display local time tied to UTC, the leap second may be inserted at the end of some other hour, depending on the local time zone. A negative leap second would suppress second 23:59:59 of the last day of a chosen month, so that second 23:59:58 of that date would be followed immediately by second 00:00:00 of the following date. However, negative leap seconds have never been needed since the UTC standard was established, and are highly unlikely to ever be, because the Earth's rotation speed varies in response to climatic and geological events. UTC leap seconds are irregularly spaced and unpredictable. Insertion of each UTC leap second is usually decided about 6 months in advance by the International Earth Rotation and Reference Systems Service, when needed to ensure that the difference between the UTC and UT1 readings will never exceed 0.9 seconds. 26 positive leap seconds have been scheduled so far. History. About 140 AD, Ptolemy, the Alexandrian astronomer, sexagesimally subdivided both the mean solar day and the true solar day to at least 6 places after the sexagesimal point, and he used simple fractions of both the equinoctial hour and the seasonal hour, none of which resemble the modern second. Muslim scholars, including al-Biruni in 1000, subdivided the mean solar day into 24 equinoctial hours, each of which was subdivided sexagesimally, that is into the units of minute, second, third, fourth and fifth, creating the modern second as 1/60th of 1/60th of 1/24th equals 1/86,400th of the mean solar day in the process. With this definition, the second was proposed in 1874 as the base unit of time in the CGS system of units. Soon afterwards, Simon Newcomb and others discovered that Earth's rotation period varied irregularly, so in 1952, the International Astronomical Union defined the second as a fraction of the sidereal year, because the tropical year was considered more fundamental than the sidereal year. In 1955, the IAU redefined the second as the fraction 131,556th, 925.9747 of the 1900.0 mean tropical year, which was adopted in 1956 by the International Committee for Weights and Measures and in 1960 by the General Conference on Weights and Measures. becoming a part of the international system of units. Eventually, this definition too was found to be inadequate for precise time measurements, so in 1967, the SI second was again redefined as 9,192,631,770 periods of the radiation emitted by a cesium-133 atom in the transition between the two hyperfine levels of its ground state. That value agreed to 1 part in 1010 with the astronomical second then in use. It was also close to 1/86,400th of the mean solar day as averaged between years 1750 and 1892. However, for the past several centuries, the length of the mean solar day has been increasing by about 1.4–1.7 milliseconds per century, depending on the averaging time. By 1961, the mean solar day was already a millisecond or two longer than 86,400 SI seconds. Therefore, time standards that change the date after precisely 86,400 SI seconds, such as the International Atomic Time, will get increasingly ahead of time standards tied to the mean solar day, such as Greenwich Mean Time. When the Coordinated Universal Time Standard was instituted in 1961, based on atomic clocks, it was felt necessary to maintain agreement with the GMT time of day, which, until then, had been the reference for broadcast time services. Thus, from 1961 to 1971, the rate of atomic clocks was constantly slowed to remain synchronized with GMT. During that period, therefore, the seconds of broadcast services were actually slightly longer than the SI second and closer to the GMT seconds. In 1972, the leap second system was introduced so that the broadcast UTC seconds could be made exactly equal to the standard SI second, while still maintaining the UTC time of day and changes of UTC dates synchronized with those of UT1. By then, the UTC clock was already 10 seconds behind TI, which had been synchronized with UT1 in 1958. But had been counting true SI seconds since then. After 1972, both clocks have been ticking in SI seconds, so the difference between their readouts at any time is 10 seconds plus the total number of leap seconds that have been applied to UTC. Insertion of leap seconds. The scheduling of leap seconds was initially delegated to the Bureau International de Jour, but passed to the International Earth Rotation and Reference Systems Service on January 1, 1988. IERS usually decides to apply a leap second whenever the difference between UTC and UT1 approaches 0.6 s. In order to keep the difference between UTC and UT1 from exceeding 0.9 s, the UTC standard allows leap seconds to be applied at the end of any UTC month, with first preference to June and December and second preference to March and September. As of July 2015, all of them have been inserted either at the end of June 30 or December 31. IERS publishes announcements every 6 months, whether leap seconds are to occur or not, in its Bulletin C. Such announcements are typically published well in advance of each possible leap second date, usually in early January for June 30 and in early July for December 31. Sometimes signal broadcasts give voice announcements of an impending leap second. Between 1972 and 2012, a leap second has been inserted about every 18 months, on average. However, the spacing is quite irregular and apparently increasing. There were no leap seconds in the 7-year interval between January 1, 1999 and December 31, 2005, but there were 9 leap seconds in the 8 years 1972 to 1979. Unlike leap days, UTC leap seconds occur simultaneously worldwide. For example, the leap second on December 31, 2005 23:59:60 UTC was December 31, 2005 18:59:60 in the US. Eastern Standard Time, and January 1, 2006 08:59:60 in Japan Standard Time. Not all clocks implement leap seconds in the same manner as UTC. Leap seconds in Unix time are commonly implemented by repeating the last second of the day. Network Time Protocol freezes time during the leap second. Other experimental schemes smear time in the vicinity of a leap second, slowing rotation of the Earth. Leap seconds are irregularly spaced because the Earth's rotation speed changes irregularly. Indeed, the Earth's rotation is quite unpredictable in the long term, which explains why leap seconds are announced only 6 months in advance. A mathematical model of the variations in the length of the solar day was developed by F. R. Stevenson and L. V. Morrison, based on records of eclipses for the period 700 BC to 1623 AD. Telescopic observations of occultations for the period 1623 until 1967 and atomic clocks thereafter. The model shows a steady increase of the mean solar day by 1.70 milliseconds per century, plus a periodic shift of about 4 milliseconds amplitude and period of about 1,500 year. Over the last few centuries, the periodic component reduced the rate of lengthening of the mean solar day to about 1.4 milliseconds per century. The main reason for the slowing down of the Earth's rotation is tidal friction, which alone would lengthen the day by 2.3 milliseconds century. Other contributing factors are the movement of the Earth's crust relative to its core, changes in mantle convection, and any other events or processes that cause a significant redistribution of mass. These processes change the Earth's moment of inertia, affecting the rate of rotation due to conservation of angular momentum, sometimes increasing Earth's rotational speed. For example, glacial rebound shortens the solar day by 0.6 milliseconds century, and the 2004 Indian Ocean earthquake is thought to have shortened it by 2.68 microseconds. It is evident from the figure that the Earth has actually sped up since the initiation of the current system in 1971, and the rate of leap second insertions has therefore been decreasing.